So now we're going to look at the definite integral and its application, which is the area under a curve. So if you had a very complicated curve and you wanted to say, ooh, let's look at this very complicated curve, 2x plus 3. Well, 2x plus 3 is just a line. And what that integral is going to do is it's going to, so there we've got our line 2x plus 3. And when we find the integral between 1 and 2, we're going to find that area that's enclosed from that curve down to the axis and those lines that you have listed right here. In this case, it's not too exciting because you could have figured this out before, probably by making it into a rectangle and a triangle, and you would have the skills to be able to figure that out. But if it was something that wasn't so neat, like a parabola or a cubic function, that would be very hard to figure that out, then this becomes very cool because you get the actual area under that quite easily. So here's our first example. Here's another line, y equals 2x plus minus 1, the x-axis, and the lines x equals 1 and x equals 5. So this is a definite integral. We can set it up that way. And then look at integrating. But this time, because it's a definite integral, we don't have to write plus c. All we have to do is figure out the integral and then write the numbers 1 to 5. When we evaluate that, we plug in 5 first and then plug in 1 and subtract them. So we end up getting 20 units squared. And there's a picture showing what we just did. Basically the same thing that we looked at before. Now we can do this on our graphing calculator as well. So what I'd like you to do is I'd like you to graph 2x minus 1 into your graphing calculator. And what we're going to do is we're going to get it to look like this. So how do we go about that? Did you learn that last class? How to do the shading and stuff? So you're good with that? Okay. And I won't go over it right now. There's just a window. So you graph it, and then under your calculate menu, the same place where you got your maximums, your minimums, your intersection point, the very last one is an integral, and then you can find the integral between two things, and it calculates it. For right now, it's going to be just really nice to use as a check. You're going to do it by hand, and then you can type it in your graphing calculator and check, did you get the same answer? A little bit more complicated, 15 minus 2x squared. Integrate that one between negative 2 and 2. Again, the integral itself isn't hard to figure out. Plug in 2, subtract negative 2. Now with this one, before simplifying things completely, there's going to be some stuff here that might work out to put together sort of like fractions that are more like terms. So it might be easier to simplify that before I simplify in the brackets completely. And this is one of those times where you got the 30 plus 30 can make 60, and then you can estimate it. Again, there's the idea. And that's a much neater idea than under the line, because this would be hard to calculate any other way. And we get the same results. So sorry about our notes here, got a little crazy with the things going at the bottom and then you got space on the next page. But try this one. I'll come around and help you with the integrals. All right, so we integrated here. We got sine x plus x from 0 to pi. Plugging those things in and using our values from our pi plate, we find out the area is pi. Looking at a graph, we've got this section right here. I want you to do an experiment while you're finishing this one up. I want you to experiment with the integral of cos x. So here's a graph of cos x. And we're going to go from 0 to pi. So that's going to be this and this. And I want you to not do it by hand. I want you to just type it in your graphing calculator and get the answer. Looking at the picture, make an estimate of what you think the area answer is going to be, and then check to see what your calculator comes up with. What are some of the values that your graphing calculator told you the area was? See, got one here that said, okay, from 0 to pi, 3.21 e minus 14. Or is it negative 3.21? Did everybody get this exact same answer? What does that answer mean? Do you see that it's really, really small? Because that e to the minus 14 means that we've got 1, 2, 3, 4, 5, 6. Wow. That's a lot of zeros. So if we have that many zeros, basically we can say that this is equal to 0. And perhaps our calculator has some sort of mechanism in it that it's not quite right, because the integral here is actually going to be 0. But when we look at that, I see an area here and I see an area here. What is happening? Why is that equal to 0? Because if I would estimate how much area I see, I would tend to think that that's a lot more area than 0. So some things that we need to learn about our definite integral. And the first point here, if a function is negative or below the x-axis over a certain interval, then the definite integral is going to find that area to be negative. So if we think about the example we just did, does it make sense that it's symmetrical and half the area was above and half the area was below? And so if one of those is positive and one of those is negative, well, when you combine them to add them all up, you're going to get 0 as an answer. So all that negative sign is saying is that the area is underneath the x-axis. So if you wanted to find that actual area, you would have to do it in two little sections. We would have to do the section from 0 to pi over 2, and then do the section from pi over 2 to pi. And because that section would be negative, we could take the absolute value of it to make it positive. So sometimes we're going to have to do different little sections. We're going to have to find out where that x-intercept is to see that some of the areas is below and some of the areas are above. So here's our first example, x squared plus 4x. And we're looking for, this question is worded as it says, find the area between the function and the x-axis. So it's a different question than just asking for the definite integral from 0 to 2. Because the definite integral from 0 to 2, you'd keep the things that are negative, negative, you'd keep the things that are positive, just like we did with that coast graph, and you'd get an answer of 0. But this question is saying, find the area between the function and the x-axis from negative 2 to 0. Well, if we draw a picture of it, it's going to be, all that area is going to be below the x-axis. And so when we do the integral, we know that we're going to get a negative answer. So we can put absolute value bars around it, because it's going to be negative. Then when we solve it, it's going to become positive. So here I'm just doing the work with the definite integral. You can see that we're going to get a negative answer. And once we get that negative answer, we can take the absolute value of it to say that the actual area is 16 over 3. But if you would do this one on your calculator would come up with a negative area. So now that same function, so here's the graph again, but now we're looking between negative 2 and 2. So we see that that first part, we already figured out that was below the x-axis, that was the negative area, and the other part's going to be a positive area. So if you just did the integral from negative 2 to 2, those areas are going to cancel each other out, and you won't even notice that you're not actually solving the question. So again, it's very important to have a visual of this, to see the graph, to recognize that we have an x-intercept at 0. So we're going to figure it out from negative 2 to 0. That's the negative part, and we're going to do the absolute value. Then we're going to add from 0 to 2, and that part is going to be the positive part. Now we already did that first part, so we knew it was 16 over 3. And this area from 0 to 2, if you worked it all out and plugged it in, you'd get 32 over 3. So you're going to get a final area of 48 over 3. So here we have a curve. This curve can easily be factored because there's a common factor of x. And then we find out that there's 3 x-intercepts. So 0, 1, and 2. Now if we're going to find the area of this curve between 0 and 3, can you see that both the yellow and the blue areas, they're above the x-axis, but the green area is below. So you're going to have to find out each section separately and then add them all together. So this is just saying I'm going to find, and I just wrote y instead of having to write the whole thing out each time just to make it shorter. So we go from 0 to 1. Then we're going to go from 1 to 2, and I've got absolute value bars around that already because I know that that section's my negative section. And then go from 2 to 3. Now there's going to be some times that you might not be able to visualize the graph, and you won't know which ones are the positive sections and which ones are the negative sections. It's okay to do your work, and then you're going to find out, oh, these two are positive, this one's negative. And then later you might go back and add absolute values all the way through to make it look like you knew right from the beginning, even though maybe you didn't. So just saving you some time of actually figuring this all out, we're going to find out that those sections are 1/4 plus 1/4 plus 2.25. And again, if you had a calculator, it would probably make sense to graph it and figure out those ones using your graphing calculator, because it would be so much quicker than figuring it all out by hand. So again, depending on what you're allowed in a question, the graphing calculator can save you a lot of time, because there's going to be some questions on your exam that you'll need a lot of time. So wherever you can save time, it's going to be important. So here's the idea. My graphing calculator, find the area between 0 and 1, find the area between 1 and 2, and then find the area between 2 and 3.